Good morning, everyone. I'm Ali Olivier from the South African Mathematics Foundation. I've been involved with mathematics Olympiads and competitions since 1997. So it's a privilege to host this session this morning. We're going to look at when mathematics meets art, presented by two of my colleagues, Catherina Steyn and Prof. Werner Olivier from the Govan Mbeki Mathematics Development Center at Nelson Mandela University. Thank you. We look forward to your presentation.
Thank you very much, Illy, and thank you everybody for attending here. It's nice to see everybody. Just for information, I will be presenting today, and my Werner Olivier will just be assisting or helping with the answering of questions, maybe also looking at the chat if possible. But thank you very much, and I look forward to sharing a little bit about our journey with maths and art. And if you have any questions, you're welcome to pop them in the chat or otherwise at the end of the session. As I've already said, I'm going to do a little demonstration. I would like some of you to also take part in this demonstration later on in my talk. So if you do have just a regular piece of, it doesn't have to be an A4 piece of paper, but just a piece of paper, a ruler and a scissor close by, as well as a pen, that would be very helpful or to take part later on. I'm going to share my screen and then let's get the ball rolling. Okay, there we are. Okay, my talk is when maths meets art, and is it even possible? First of all, I just would like to say a little bit about where we came from, which was Steyn, and then we're going to look at some math art tessellations. Now, first of all, what is Steyn? It's a new educational approach, and it's actually an international trend there's an international trend towards Steyn. At our center, we are continuously researching mathematics education trends in the world, and the front runners of mathematics education, the Finnish people, Chinese, people from Singapore, we've looked into their systems, and although their whole system is quite different from ours, we decided to look at elements that we can use in South Africa to help our situation. Now, previously, or the subjects that it was known as STEM, so science, technology, engineering, and mathematics. What we're currently doing now, what currently is being done, is adding art to this mix. And this, as I said, is at this stage a focus of what we're doing at the center. Now, the original STEM, science, technology, engineering, and maths, was already a step ahead from what we traditionally did in the traditional maths or the classes, different classes. We taught the subjects in, let's call it silos. So in the maths class, we taught maths, and we didn't really bring in any science concepts or science. We didn't really mingle technology and engineering with maths and with science. But what happens in the STEM mix is where we start bringing in the other subjects as well. We mix them with real life situations and problems, and it's a lot less teacher-centered, so more a learner-centered approach. Now, why are we combining maths and art, first of all? So now to move away from STEAM. So STEAM was what initially brought us to this. What researchers found is that there's a huge positive influence in including art in the performance of learners and in the development of the STEM subjects. There's a need to think more creatively, and I think with just the recent pandemic that we're still currently in, we need innovators in South Africa. And I think that there has been very little other time in South Africa where we've had so much change taking place so quickly, and we've had to innovate, create, do things differently. And the combination or combining art into this mix stems or creates creativity or brings up a different way to think about things. We wanted, through our combination of maths and art, and we did this in a math art competition, explore maths and art in a different manner. And what motivated us to keep on doing this was the responses that we actually received from teachers and learners during the competition. And if you want to know a little bit more about that, you're welcome to later on to go to our Math Art website and then also investigate a little bit more of what we're doing in this competition. But let's go back. We all know that we use visual pathways when we work on mathematics. However, in most of the teaching at schools, mathematics is taught as a subject of numbers and symbols. So people don't really use pictures or art to teach mathematics. However, mathematicians rarely, if ever, solve a problem without some kind of visual representation. If it's either whether it's doodling or trying to draw out the process of a problem, people often use, or mathematicians mostly use, visual representations. And I think we all need to develop the visual areas of our brain. So we often get said, or people say to us when we start with a competition, we are mathematicians, we can't think creatively, therefore we don't know whether this competition is for us or maths and art. How do you combine that? But we found that there's a need amongst the learners as well to become more creative. And on the screen at this stage is a quote of one of our grade 12 learners from the Eastern Cape that said, learners with a more creative way of learning struggle in class because the way mathematics is being taught is rigid and set in the past. Another learner said, at my school, we do not have the opportunity to nurture our skill in the arts, design, or mechanics and engineering. And this deprives learners like myself an opportunity to get a head start, to get the necessary foundation. So the learners are needing this as well, the combination of creativity in the maths class. Now, as I said, normally when we start out with a competition, everybody says, I'm a mathematician, I never could draw. And when we talk to the art people say, my goodness, I never could do maths. I dropped maths as soon as I can and quit at school, so I've stopped doing maths at all or completely. However, if we look at the following words, for example, the word lines, do you think this belongs to maths or does it belong to art? What about the word curves? Maths or art? Shape, dimension, proportion, scale, perspective, size, parallel, mirror image, line of symmetry, and I can continue. I think that all of you will realize that as we look at these words, they're used both in maths and in art. So maybe the two are not so different from each other. And maybe we should bring in a little bit more creativity in our maths teaching. So what about using Kandinsky when you teach circle geometry? Who said that teaching this typical grade 11 circle geometry theorem, angle at the center of the circle is twice the angle at the circumference, has to be represented in a boring black and white drawing? If we look at this beautiful representation that a learner did call the sacred aloe, isn't this a beautiful way to represent that theorem? And then also to indicate that no matter where on the circumference of the circle you're looking at, the angles are exactly the same size. Why not really make geometry fun by using the parallel lines of Esther Mtlangu? Why not explore maths in culture? And we can even draw with graphs. The most beautiful artworks, or some of the most beautiful artworks that are created, are actually used drawing graphs or using graphs. Now, in our workshops that we present to promote the maths and the art, our objectives are normally to make learning fun. So today as well, I'm just going to demonstrate or illustrate to you a little bit of what we do in a workshop. So there are obviously a whole host of different ideas, but we're just going to look at a few of them. So normally our workshop objectives would be to encourage maths and art people to work together to improve innovation and creativity. So we don't just invite mathematicians to our workshops, but also artists. And we would like them to get together to improve innovation and creativity. I think often in a staff room when people teach maths or teach art, they sit in separate sides of the staff room. They don't necessarily talk together or talk about work. They might talk about personal things, but not necessarily work. But I think that should change. We also want to inspire our participants in the workshop to see the links between maths and art, and not as things that are completely separate. We also want to stimulate our participants to start looking differently at the world around them. So not just to look at maths and art differently, but actually to look at the world differently. And then we want to encourage participants to experiment more with examples in their own classes. And our workshop is really designed to illustrate a small section of combining maths and art, and then it's to stimulate people to go and do more in their classes. Now let's start with our presentation of maths and art. Now, first of all, a transformation. I want all of you to have a look around you in the room that you're sitting at right now. So transformation, first of all, is a general term for 4 specific ways to manipulate either a point, a line, or a shape. So changing a shape using, for example, a turn or what we call a rotation, a flip or a reflection, a slide or a translation, or a resize or an enlargement. Okay, I want you to have a look around you in the room that you're sitting at right now. Can you see any examples of things that have been turned or flipped, slide, or resized around you? Okay, maybe it's not so easy to think about it when you think initially, but I want to ask you, can you see a cupboard somewhere? Maybe you're in a room with a cupboard with doors to it. If you have a look at the 2 doors, the one handle faces one way and the other handle might face the other way. So isn't that an example of a reflection? So one door is reflected in another door. Have a look around you as well. Maybe you have 2 doors that are next to each other, but not necessarily the 2 handles facing towards each other, but put up differently or attached differently. Then you have a slide or a translation. There might be something smaller and something bigger in your room. If you're sitting at the dining room table today, you might see in the dining room chairs around the table an example of rotation. So the one chair faces one way and the other one is placed 90 degrees to that, so that is rotated. So examples of transformations and rotations in the room that you are sitting in. The original shape of an object is called a pre-image, and this is something that we use in maths, but it's also used in art. And the final shape of the position is called the image under transformation. And something else I'd also like to combine today in our workshop is tessellations. Okay, so now what are tessellations? They are arrangements or tilings of shapes that cover a whole surface without overlapping or leaving any gaps. And as you can see from the example here in my picture, you can see that there is, let me just quickly go there. Okay, if we look at, for example, this bit, sorry, oops, here, you can see the tiles at the bottom. We can see those bird pictures where they closely fit together, but they don't overlap. And I'm sure if you look around in your room now, you might have tiles on the floor or even tiles or different pieces of the roof that tile together without any gaps. And tessellations are not just man-made, they are also in nature. Have a look at those beautiful patterns on a lizard's leg, or the patterns on a giraffe. Another example of tessellations is in the cells packed closely together on a leaf, or the hexagon shapes in honeycomb, the patterns on a pineapple, the tail of a chameleon, and then of course a tortoise shell. We also have man-made tessellations in the different buildings, beautiful buildings. Each face of the polyhedron of that top figure there, which is the big building in Epcot Center in Disney World, was designed to form, or from isosceles triangles that were designed to form a point. And the cladding that was used on that building was designed so that when it rains, no water pours off the sides onto the ground, but the water is all collected through 1-inch gaps in the facets into a gutter system. And I think that's quite nifty. And this is a beautiful building, so combining art and beauty, mathematics and engineering. I think this is a super example of what STEM can be used for. And then also solving the problem of collecting water, which then can be used in fountains and in the little rivers and all of the other things at Disney World. Now, tessellations, mathematicians have shown that only the following regular polygons can be used for tessellations: a triangle, a square, and a hexagon. Now, why only these regular polygons? Why do these? Now remember, a rectangle is not a regular polygon because its side lengths differ. A regular polygon is something that has equal side lengths. So why do only these regular polygons tessellate? Because their angles are a factor of 360 degrees. So a triangle has an angle of 60, square 90, and hexagon 120, and those are all factors of 360 degrees. So when you pack them closely together, they form 360. Now, an artist that used these basic shapes in his tessellations, but also distorted them, was Escher. Maybe some of you are familiar with Escher's work, but let's have a look at one of the examples. Now, sometimes Escher changed the basic shapes. For example, starting out with a simple square. Now, by distorting these basic shapes, he changed them into animals, birds, and other figures, and the effect can be quite both startling and beautiful. So let's have a look at what he did. He, for example, would cut out a piece at the bottom of the object and then attach it to the top. So cut out a piece at the bottom of the square, attach it to the top, cut out a piece from the top, and attach it to the bottom. Then from the left, and from the right as well. And if you do this, you will get a pattern, and he also, of course, also decorated it, which then, when you tile it, fits closely together without leaving any gaps. And doing this, he could create the most beautiful drawings. Here, as I said, is just one example of what he did, called Escher's Horses. Unfortunately, it doesn't have such a creative name as the beautiful drawing that you see in front of you, but this is one of his very well-known pictures using tessellations. In our workshops, we then also play around with tessellations, and this is a bit difficult for everybody to collect and to get together, so I'm just going to show you an example that is so easy to do and something that you can have a look at later on. These presentations will also be shared via the platform, the STEMI platform, so you can go and try this at home. So you can start making your own beautiful tessellations by beginning with a simple geometric shape. Now we start with something on a cardboard square. So I don't know if you can still see the camera, on a cardboard square, and then we start out and we make a template of a little fish. And then this little fish is then cut out onto pieces of paper and then used to draw a tessellation or something similar to what Escher did. Now let me show you how to do it very simply. Take the piece of cardboard, and on the one side of the cardboard, you draw in a triangle. Now, if we just look back at the previous page, that triangle eventually is going to form the tail part, and then on the other side, the head of the fish. So you draw in a triangle, and then you cut it out and attach it to the left of the little square. And there's an illustration made up in GeoGebra as well. So it's cutting out the triangle on one side, attaching it on the other. Now, you take the same piece of paper or same little square, a cardboard square, and you draw little triangles at the bottom of this shape. It's also then cut out and attached to the top. and then you use the template. So what you've created now with your cardboard is a little template that you can use to cut out fishes on colored paper. And I'm just going to show you an example of what the learners did on one of our workshops when they pasted these altered fishes onto a piece of paper. So the exact same pattern that we had in the previous slide, cutting out a little fish and colored paper. It was magazine pages. So we always collect a lot of magazines and then cut out beautiful colored pieces of paper or little fishes on the colored pages. And then the other pieces that you can see here, the other little fishes, were just pieces of newspaper. And one can be very creative and use all kinds of different pieces of paper. So they used the little cardboard template as a template to cut out fishes in the magazine or the colored pages and on the newspaper pages. And then they pasted these, tiled them onto a colorful background. And one can use all different, you don't have to use that same type of fish. There's another example of a fish that was also made using a similar model with little cardboard shape. There are a few more and a few more at the bottom. The one on the left hand at the bottom, by the way, was made by one of my colleagues here at our center using beautiful wax print material, some shwe as well as foil and other plain cardboard paper. And then the one on the right was something that I got from the internet using beautiful colorful paper as well. So one can really create using just these simple principles, some beautiful little shapes. However, what we want to do now is I want you to also play around with something that is a bit more complex. So with it, we're going to look at hexagons. And now, first of all, we're going to look just first of all at something or how we can tessellate these hexagons. So I'm going to stop sharing here. And I'm just going to share my GeoGebra screen. Okay, so in the same way as we little cut out pieces on a square and attached it to another side and then translated and tiled or made a pattern, you can do exactly the same with a hexagon. Now, first of all, do hexagons tessellate? So let's just first confirm that. Okay, there I've placed another piece, there I've placed another piece, and you can immediately see in those three pieces, they fit tightly together with no gaps. And if I place more pieces around the central one, you can see that they do tessellate. In other words, they fill the space completely without any gaps. So we can continue. Okay, but let's go back. In the same way, using the same basic shape, and you're going to create a basic shape with me just now on the camera, you then can change or cut out a piece, maybe cut out a triangle on the top and attach it here to the left-hand side. And once again, if you use a basic shape as a template and then use it to draw little shapes on another piece of paper, you can create a whole beautiful pattern using just that one small change to the hexagon. Now let's play around a little bit more, make a few more shapes, add a few more things. Let's put that outside there. Now I've got something that's not even recognizable as a hexagon anymore, but it makes the most beautiful pattern pieces that without even drawing things on them like Escher and illustrating them a little further, you can already create a beautiful pattern, tiled pattern, with just a simple little transformation. Okay, let's go back. Right, now I hope everybody has a piece of colored paper or a piece of paper, any paper next to you. It doesn't have to be an A4. I'm going to now, together with you, construct a hexagon on a webcam. Now, whilst I might give a few more minutes for people to collect a piece of paper, let's just have a look at hexagons in general. Now, let's see if anybody knows how you can create, or what popular sports item do you think contains a regular hexagon? Well, I hope some of you knew that a soccer ball, yes, I know it contains pentagons as well, but a soccer ball contains hexagons, and there's lots of theories about that, but also one of the facts that when you tessellate them together, it actually forms a nice round or a very almost round object. Now, where else would you find hexagons? Maybe not in the room as you're looking around you now, but for example, in a honeycomb. Bees use honeycomb or use hexagon shapes when they create their honeycombs. And the reason why we suspect is because it uses the least amount of wax to create the largest volume that honey can be stored in. So very practical. Pencils as well use hexagons. If you have a look at a pencil from the side, it's got a hexagonal shape. Now, I wonder if you can think of a reason why. Now, I think there are also quite a lot of reasons, and I think one of the first ones is maybe to be able to pack them very efficiently. If you think of how nicely hexagons tessellate, to pack them very efficiently into a small enough container. But I think it was also a practical reason. A round pencil would obviously slip or slide off a surface more easily, whereas a pencil that is hexagonally shaped won't. Nuts and bolts also use hexagons. The tool edges find it easier to grip an hexagonal edged bolt, and that means that more torque can be transferred to the bolts. Okay, so everybody ready? I hope everybody's got a piece of paper. Let's do this together. I'm going to open up my camera now, and I hope all of you can see this piece of orange paper here. Now, when you have a rectangular shaped piece of paper as I have here, how do you get a square? I think this is a relatively easy exercise. You literally normally, now remember, getting a square without using a ruler or a protractor, you could simply just fold this side over here to get a square. So that's easy. Now, why does this produce a square? Let me just use this page here on which I've drawn a line to make it easier. Why does this produce a square? Because if you look at it, you are using the one side to get another equal side there. And then you use your scissor to cut off the extra piece. So, and that way creating a square. Okay, now we fold it over an isosceles triangle. Okay, so getting a square, that was easy. How are we going to change this square into a hexagon? And if you're unsure of it, there's lots of different ways on the internet to do it. I'm just going to demonstrate one simple way. And I'm going to do this nice and slow. So I want you to fold back your square and then keep the flat or the folded side towards you, and then fold this triangle over again. So we're going to fold it in half. So making those two edges meet up, we're going to fold it in half. Okay, open it up, and now use a pen and make just a little mark at the bottom. It just makes it easier to see when you're going to fold again. Now, we're going to fold over this side as well. So we're going to now fold this sharp edge here towards the top of the triangle. But you're not going to fold it through completely. You're just going to fold that edge there to make a little mark. And then you can use your pen to add in a little mark there. There we are. Okay, fold it open again so that mark is on the back. Now we're going to fold this again. So we're going to fold over that mark on that same edge towards the top, the apex of this triangle. So we're going to fold. So there's the apex of the triangle. I'm folding it over again. So make sure, as with all origami, of course, the more accurate your folds and the nicer your folds, the more accurate your product is going to be at the end. Now this time, once again, don't rub it down all the way, just press the crease at the top here. Okay, give everybody a chance to get there. Okay, now open it up again. We can make another little mark there, and then you can use a ruler, or if you're good at a freehand sketch, to just draw a line from that mark to the center fold. Right. Now what we want to do is we want to fold over this triangle again. So now keep your finger here at the bottom where you made that first mark at the center of the bottom side of the triangle. And you're going to fold it from there. So press it down a little bit to make it easier. And then fold it over so that that mark of yours there reaches that line that you drew there. So fold it over and now completely fold that side there. Fold it down. And if you've worked very accurately, if you now turn it over, so you folded it, now we turn it over, and then we fold this side. So where that fold is there, we're going to fold it on there. And if you fold it accurately, now, when you fold over that side there, these two sides should match up as well. So these two sides here match up when you fold it on the side. Now you get something that looks a little bit like a flower. Now, once again, get your pen. And I want you to just make a little mark there. So at the tip of that page there, make a little mark there. And then transfer that mark to the back. And then go all the way around to the other side. So that when you turn it around, you have a mark on this side. Okay, there. And then on this side here, just make a mark where that page or that tip is there. The markings just makes it easier to draw a line. Now, taking up your ruler again. You join that point there. You draw a line straight across. Like that. Okay, we're almost done. All that's left now is to use a pair of scissors and to cut across here. So we're going to cut off that piece there. Now, if you don't have a pair of scissors nearby, all you need to do is you can just fold. So you just fold that piece back to make a fold line there so that you can still see that line. So if you don't have a pair of scissors, that's okay. Just fold that over on the line that you drew there. And when you open this up, voila, there we have a perfect hexagon. A regular shaped hexagon, which means what? All the side lengths are the same. And what does the hexagon consist of? I'm just going to put this one here. I've drawn a few lines just to make it a little clearer. All the side lengths are equal. So if we look, for example, here, this side length there, it's the same as that length there, the same as that one, the same as that one. So what we've managed to do here is we have managed to draw 6, 1, 2, 3, 4, 5, 6 equilateral triangles. And this is what a hexagon consists of, 6 equilateral triangles. And those 6 equilateral triangles one can then, for example, work with learners a whole lot of questions regarding this. For example, what are the sizes of the angles? 60 degrees, the 60-degree angles all add up to 360. So the triangles all tessellate as well, and a whole lot of maths. One can then use your basic template, as I illustrated just now, and cut out sections from the top and add it to the bottom to make those beautiful patterns as we saw. So let's just demonstrate that. I've cut out a triangle piece from the top, and by adding it to another side there, I can create another pattern piece, but you can also attach it there. So there are a huge amount of possibilities of what you can do, and then make the most beautiful patterns creating or using these hexagon squares. Okay, let's go back. Right. So questions that one can ask further questions about this, and to draw this back into your maths class. What is the shape of the triangle surrounding the midpoint of the regular hexagon? As I've already said, learners can then measure the angles, measure the side lengths. How do you determine the area of a hexagon? Maybe this is a bit more complex. Something that you could ask your learners, how would you determine the area? And this, once again, very useful. One of the biggest problems that learners have is actually working out an area of an object that they can't see the height of. So to demonstrate or to illustrate for them that where to get the height of the triangles, and then do you need to work out the area of each triangle, or can you simply work out 1 multiplied by 6, etc. So working out the total area of the hexagon that you created. There's also a lovely, but I think I won't have time, beautiful thing in GeoGebra using this link here that you can go to try and to explain that a little bit better to your learners. I think there's still just a little bit time left for questions. Ellie, I don't know how my time is doing.
You're doing fine, Catherina. You still have about 5 minutes, but we can move on to questions if you're done.
Okay, so right, great. Let me first ask, is there anybody who has any questions, or maybe something that was in the chat? I haven't had a chance to look at the chat right here.
There was only one request, actually, is whether you can share that illustration, how to make the hexagon. There are some people, some teachers that would like to do it with their learners.
Okay, great. Yes, I will. I think that the recording of this presentation will also be shared most probably on the STEMI channel. So then people are welcome to have a look at that. Also, if you go to YouTube and you simply just type in constructing a hexagon or folding a hexagon with paper, there are a whole lot of different examples. This, as I said, is just one. When I did this with some learners, the learners actually Googled it, and they came up and they said to me, ma'am, I think there's another way to do this, and my way is easier. And some of them came up with other creative ways, which is also possibly something that one could throw out to your learners. So ask your learners, how else could you fold a hexagon? And then also, as I said, with regards to when you fold a square, which is something easy, and a hexagon is more complex, how exactly, with the square it's easy, you try to get the two side lengths the same. How do you get a hexagon? And that would be easy, of course, if you know how to divide a page into 6 equal parts. So that's another more complex question that one could also throw out at learners or children or even adults, students.
For those you've logged in earlier at 9 o'clock, there was a video playing, and they showed a lot of the artworks that was submitted by the learners. I'm fortunate I have your calendar on my desk, so it's I can look at every day while I'm working. Have you made a decision on this year's winners?
Thank you. Yes, Ellie, we've finished the judging process. What we're doing currently now is we're collecting. We're asking teachers to post in the final artwork. So the final round judging has already taken place, but we need to verify that the artworks are actually authentic and hand drawn by the learners themselves. So we ask them to post the artworks to us, the final round for artworks. And then soon after that, there will be a prize giving, as well as the winners will be announced on social media and our Facebook platform. For people who want, as I said at the beginning, once again, just a bit more information on the math art competition. So our math art competition runs every year at the beginning of the year from January. We start in January with the promotion. February, we do our workshops, but the actual entries open at the beginning of March every year. So the 1st of March, and then learners have right through March and April to complete their artworks and then to put them into, or to enter them into the competition. For the competition, we have a specific math art website where the learners then enter online. We designed the website to be data light, so learners don't need a lot of data. They can take a picture of their artwork with their cell phone cameras, and then there are 3 questions that we ask them just to try and drill down a little bit more into which maths they used to create their artwork. So for example, this year's theme was beautiful mathematics, and the learners had to think of what beautiful mathematics meant to them. And if you look at the video, or as Elias mentioned, there was a video playing in the general session this morning about, or with some of the artworks in them. You can also see the different artworks from different years, just a selection of them. But we get hundreds of these artworks in from all over South Africa. All grade 7 to grade 12 learners enter, and they are then judged in the different categories. So for us, it's been absolute learning experience with learners, teachers, just seeing how people think about it. Christoph in his talk yesterday referred to not just being maths and art, but learners also used this platform to express their frustrations with last year, the current world happenings with the pandemic and the coronavirus. They used the artworks to express their frustrations with mathematics. Learners also use the artworks to express their joy in doing mathematics. And we have beautiful artworks where learners really drill down into complex things such as, which is not done at school, fractals, the Kuramoto model of mathematics, synchronization of things, the Fourier transformation. So lots of more complex mathematics as well, which then obviously stimulates learners to think more deeply about mathematics. So beautiful artworks that we really enjoy, and we enjoy what learners do. Also something that we've really learned from the artists. I think we as mathematicians don't necessarily look so deeply into the things around us, but artists learn to really look at something. If you want to draw something, you must really look at it and study it. And this is something that we've learned from the artists as well. So I don't know if any of my colleagues who are in the meeting would like to say something or just unmute themselves.
Yeah, Ellie, Karin, thank you very much. Wonderful, presentation. And clearly there's so much more to support STEAM education. But this particular context is, I think, very well, showcased. And I just wanted to mention, I put it in the chat as well, that, people can actually go to our YouTube channel. There are very number of other things linked to math art as well that they can access just for reference purposes. Thanks, Karin.
There's a question by Flora Olivier. Flora, you can go ahead.
I just saw in the chat here was a question that popped up now on my screen. I think Flora maybe just wanted to give a comment. So it's interesting as tessellation starts early. It's from Emma. Question: does this mean intermediate phase cannot participate in the competition? I hear it's from grade 7 and up. Emma, you're right, at this stage, the competition is just from grade 7 and up. If we have a sponsor that will help us to extend the competition to the earlier grades, then we can do that. So at this stage, if any of you know of any sponsors that are willing to help us sponsor this competition with primary school learners, then we can also consider doing that. But we started with the grade 7s as they fall into the phase of the senior school. But yes, it's not at this stage something that we are doing. Or the intermediate phase is not in the competition as yet. Are there any
other questions or comments? Catherina, one of the objectives of the conference is to extend the reach. Can you tell us more about how many learners are participating?
Well, we've had quite a number of learners this year. We had so almost 400 people registering for the competition, learners from all over South Africa, which was a little less than we expected, but we had quite a few challenges with the pandemic, and a lot of our learners are the junior learners in the grade 8s and 9 sections, which we all know that they didn't attend school every day. But from our previous years, our competitions were up to more than 700 learners per competition. So the reach of the competition, it's a bit difficult to judge. So the final entries that we have in the competition are obviously less. What a lot of schools and districts do is they have in-house competitions. So the teachers don't enter all the learners into the competition. They would give this as a project, the competition as a project to their learners, especially the grade 8s and 9 teachers in arts and culture are often looking for projects for learners. So they will link up with a maths teacher and have all the grade 8s and 9 learners enter. And then they only select after their in-house or in-school competition, the best learners. We encourage everybody to take part, but we find that schools select learners and then enter only the best. We also have various art centers that help learners throughout the country, also entering their top students into the competition. So the reach at this stage, we have entries from all over South Africa, but the numbers, the exact precise numbers of all the people who take part is a bit difficult to say.
I wonder if I can just add something to that. The competition is completely online. I don't know if you've mentioned that, Catherina. It's important because we fully integrate technology to make it easy to submit, So this is definitely forward-looking. Clearly, it was affected quite heavily by the pandemic, last year and this year. So we hopefully will have a much, much better situation and participation and reach in the future from 2022 onwards.
Yes, now our numbers for the Mathematics Olympiad and the Math Challenge also dropped because of the pandemic. So we hope that things will normalize by next year, hopefully. Any further questions or comments before we wrap up? Catherina, many thanks for your presentation. I'm sure everyone enjoyed it. If I look at the comments, it's clear that the delegates enjoyed the session. So many thanks for that.